Hello everyone, we are looking into seismic reflection method of investigation, and that toward the end of my previous lecture we had a look into this slide in which we can determine the angle of dip of the formation if you do seismic reflection survey as shown in this picture, right. That means I will redraw, right. In this case what we are doing is we have a source at the center and the geophones are arranged on either side of the source, which means we are able to have the signals recorded on either end. If the bedding plane is horizontal, at correspondingly kept geophones on either side, the signals have to reach at the same time, right. Suppose here the signals are reaching at 10 milliseconds on the right hand side also, since they are kept at the same distance on either end, the signals will reach at 10 milliseconds, right, provided if everything else is fine, right. Now we are receiving signals at 7 millisecond here, at 10 millisecond here, which indicates the formation is inclined like this. That is why it is traveling only shorter distance gets back to this receiver in 7 milliseconds, whereas here formation is at some additional depth, greater depth, so due to which it takes 10 milliseconds. So with this time lag we are able to determine the angle of dip, which is sin theta equivalent to V1 multiplied by delta t by 2x. What is delta t? Delta t is the time difference between these. In this picture, what is the time difference? 10 minus 7, which is 3 millisecond, right, divided by 2 times of the distance between the source and the geophones. So using this relationship we can determine the dip of the formation, which is below the ground surface, which is invisible to us, right. We are carrying out the investigation at the surface. It is interesting, isn't it? Similarly, we can arrive at the average velocity, since we would have used geophones we would have placed geophones at different distances, due to which we can determine the average velocity using this relationship. So squares of the times and distances are plotted against each other, and inverse of the slope of the line gives you the average velocity. That means we can give you a plot of square of distances versus square of arrival times, right. So inverse of slope of this line gives us the average velocity. So this is how we can determine the average velocity by seismic reflection survey when the formations are dipping, right. We had a look into this in the previous lecture. Now we will continue with another interesting method of carrying out the investigation, which is often called as CDP, which is common depth point sounding or common reflection point sounding. As you see in the picture here, we have number of short points as well as detector locations. So these are the short points or the sources. We may have more also, right. And correspondingly we have the receivers at the same distance from the center point of the spread. This is the center point or the midpoint of our spread, right. Common midpoint. We place source here. If it is at 10 meters, for example, the receiver is also at 10 meters. Then the next source location is, let us say, 20 meters. On the other side we have the receiver 2 at 20 meters, right. So this is how when we do the survey, then that type of seismic reflection survey is known as CDP, right. What is the advantage of this? When you do such a thing, with an appropriate time shift called as move out. That means what we do is, what is the time advancement when you increase the distance? Here you got at, let us say, 10 milliseconds. So, here you are getting at 11 milliseconds. That means it has taken 1 millisecond more because of the distance, isn't it? So, this is what is known as move out, right. We can provide kind of move out correction, that is the two traces S1 to R1, S1 to R1, right, sorry, S1 to R1 and S2 to R1, S2 to R1, right, S1 to R1 or R2, S2 to R1, right. That means, I will repeat, right, with the appropriate time shift, which we call it as normal move out correction. That means, we try to correct for the times, right. How are we going to do that? So, if you look at the two traces from source 1 to R2, right, that is what is source 1 to R2, right, from here to R2. Then the next trace is from S2 to R1. We have two traces, right. So, we will be able to carry out a simple correction, right. That means, from here to here and from here to here, we can correct this data in such a way, right. This helps us in enhancing the reflected energy by cancelling the other noise. We will be able to arrive at on our own the arrival times, right. Using this, we can have a check of understanding whether we are receiving any noise or not. That is the advantage of common depth point sounding, right. Then what are all the other methods of sounding, right? Just now we had seen common depth point sounding. Then the other method of carrying out the seismic reflection survey is fan shooting. It is similar to what we had seen already. This is the source and receivers are kept at the same distance around the source, as you see in the drawing which I am making. All the receivers, this is R1, R2 and so on, right. They are all at same distance. This distance is only x, right. They are at the same distance. So, when I draw this lines linking the source and receivers, this resembles like a hand fan, okay, like a small fan. That is why this method of shooting is known as fan shooting. Suppose if the formation below or the interface below, I will draw here, this is the ground surface, this is the interface. If the interface is horizontal, what will be the arrival times here? Arrival times will be the same, right. Suppose if the interface is inclined, depending upon the angle of inclination, you will have different arrival times, right. So, at the receiver, suppose if the formation is inclined, the receiver which is above the maximum inclination, that means along the true dip direction, the arrival times will be much more, because the signals have to go and meet the bedding plane at greater distance, right. Whereas, imagine at this place the formation is dipping along this direction, right. Here arrival time will be much higher. Perpendicular direction, suppose if there is one receiver here, this arrival time will be very less. So, this is how to understand the fan shooting, is done first, right? Maybe to understand the terrain, fan shooting is done as a reconnaissance or a preliminary survey. Further, fan shooting is also done to identify some bodies, some peculiar formation within the first layer itself, right? Because the signals go in and get reflected back. The velocity difference due to the presence of some different formation within the first layer will also affect the signals, right? So, fan shooting helps to identify such bodies, right? And common depth point shooting we have already seen on the previous slide, right? This is what is known as common depth point shooting. This is mainly carried out to correct the move out, what is known as move out correction, right? Making use of these true traces, we can correct the data which we have got. This will enhance the reflected energy as well as cancelling the noise. Then profile shooting. In profile shooting, we had seen already, right, along a profile, we have the geophones and this is the source. And we progress, then the source is moved here, then geophones are also corresponding source, receiver, source, receivers. So, this is how we carry on along a profile. This is known as profile shooting. So, here what we try to understand, we scan the entire subsurface. So, these are all different methods of shooting followed in seismic reflection. Now, as usual, let us now focus on to the applications of these methods, right? Seismic reflection method is mostly used to arrive at the subsurface major geological structures, right? That is why seismic reflection method is indispensable for oil exploration. In oil exploration, especially those who are attending, if you are an exploration geologist, right, for oil exploration, seismic reflection method is highly indispensable. Why? Because in oil exploration, what we search for is potential oil reservoir zones. One popular oil reservoir zone is an anticlinal structure. Anticlinal structure is something like what I am drawing, where the formation is folded in the form of an anticline, like a up-arched structure. These up-arched structures will have some weak zones in the anticlinal portion. They are the potential oil reservoir zones, pay zones, because the gas will try to escape. They will start accumulating in such zones, preferably because of a tight layer at the top, maybe a cap rock, maybe a shale, right, with the formation below is less compact and has got lot of fracture, because when the rocks fold, it will lead to lot of cracks, some tensional cracks in these portions, right, in the place where it undergoes maximum curvature. So, in oil exploration, the exploration geophysicist is deploying reflection survey or reflection method mainly to delineate such major anticlines, which are the potential oil reserves. So, seismic reflection methods are indispensable for oil exploration, mainly because of the fact we are able to decipher major geological features. What are all the major geological features? These are all the major. So, anticline I have drawn already. Synclines are just reverse of anticline. This is the ground surface. This is a synclinal structure. And faults. So, faults are major discontinuities present below the surface. This is the surface of the earth. There may be a major discontinuity, right, along which the rocks have moved relative to each other, like shear, right. This is a shear force. So, both the blocks have moved relative to each other. In this case, this block has moved upwards, this block has moved downwards, right, leading to development of a huge fracture that is known as fault. This can be deciphered using seismic reflection survey. How are we able to delineate all these features? Because we are going to have a kind of a image of the subsurface. What is the image? All the seismic signals which we have, all the seismograms are stacked with each other, that itself will appear like a image, right. So, we can determine fault closures and reefs and stratigraphic traps. Stratigraphic traps are, as I told you, in oil reserve, if you have a trap formation which is a less permeable, impermeable clayey layer, beneath that may be a sandy layer. So, in sand, oil and gas may be present because the gas is unable to escape upwards due to the presence of traps. All this can be delineated by seismic reflection survey, right. So, first is the anticline and synclines. As I told you, anticlines are the more favorable structures that can be clearly brought out by seismic reflection method. And we can also determine the orientation of the fold axis. So, fold axis is the line at the maximum curvature of the bed. Whether this axis is horizontal or inclined can also be brought out by carrying out different profile survey, right. That means, if you conduct the seismic reflection survey perpendicular to the fold axis at more than 2 or 3 profiles, we will be able to understand the orientation of the fold axis, right. Then salt deposits are easily distinguished because salt deposits are having completely different seismic velocity depending upon the soundness. Usually, fan shooting helps us to delineate salt domes, right. At number of locations in the world, salt deposits or salt domes have been deciphered by seismic reflection method. Usually, these are all functioning as cap rocks for the oil to get accumulated below the surface. So, salt deposits are usually capable of transmitting the waves or seismic signals at high velocities, and they are also very good reflectors. So, beneath the surface, when you have a dome of salt, right, this is a salt deposit, right, the reflected signal, since they are good reflectors, multiple soundings, we are able to decipher the top of the salt domes. Then faults, as I told you, can be not be very directly, it cannot be indicated by reflection shooting, but the fault zones are sometimes characterized by absence of reflection or some diffraction patterns, right. So, such a complex diffraction coming out from certain zones are probably locations of faults. I am going to show you some diagrams. From there you will be able to understand, right. So, this diffracted waveforms usually indicate the locations of faults. We can understand that by carrying out move out correction, right. We will be able to recognize the diffraction, right. The least time of arrival from the diffracted wave, we may plot the edge of the fault bed, right, directly below the surface point, right. That means the depth can be calculated from the travel time multiplied by the average velocity. Sometimes fault can also be directly picked up. Suppose, imagine this is the fault plane, these are all the rocks on this side, this has moved somewhere here. Let us imagine it has moved somewhere here, some here you have some new rock that got eroded. It would have been present some are here but got eroded. This is the present ground surface. Here you have one rock and here you have another rock type. This has moved here. Okay. So, this is how the movement has taken place. Imagine this rock is massive rock, that means velocity is high here, which means here too velocity is high. In other words, they are going to function like a major reflecting layer. So, when you do survey, here you are estimating the depth to the layers, different interfaces are estimated on this side. When you conduct survey on the other side of the fault, here too we are estimating the depths which are different. Here is the depth, estimated depth, here the estimated depth is different. This itself indicates that something fishy has happened in between, probably a fault. Right. So, this is how we indirectly infer the presence of fault by estimating the depth of layers. Suppose if you get the subsurface seismic image, the anomalies which we come across indicating the anomalous zone or the bedding planes are located different along a particular line, this is probably a fault line. This is how we can interpret, right. So, that means whenever we note some diffraction patterns, right, that too, that diffraction pattern abruptly ends, right. This is how in a image you see some diffraction pattern, but it gets terminated here. On the other hand, on the other side you have diffraction pattern somewhere here. This indicates this is a fault, right. As I was telling you, the seismic reflection methods are indispensable for hydrocarbon exploration and also in understanding the crustal structure, right. How the Earth's crust is changing can also be understood. In fact, seismic methods are widely used to determine the structural oil traps, right. That means for oil to get formed, the gas which get generated much below due to decay of carbonaceous matter, the gas will always try to escape to the ground surface, right. If it escapes, no oil can get formed, but if the gas gets trapped due to some structural anomaly or some stratigraphic traps, that means you may have a trap rock which is very fine grained with less transmission capacity through which gas cannot escape, so it will get accumulated. So, seismic method is the only method using which we will be able to identify this, right. So, seismic reflection method is the primary method used to determine hydrocarbon deposits both on land as well as under the sea, right. Hope you can recollect when we were looking into how we can energize the ground. I told you how we energize the ground when we carried out a survey in the Indian Ocean from the ship, right, on board ORV Sagar Kanya, right. So, we can understand the formations below the sea also. That means, in that case, first layer, suppose if you are carrying out a survey from a ship, the first layer is water, that is all, the rest all is the same. Then we have layer 1, layer 2 below the surface of the ocean floor, right. Then seismic reflected signals travel to greater distance, up to even 5-6 kilometers, right. So, this method is indispensable for hydrocarbon exploration, right. Let us look into some interesting results of seismic reflection, right. Almost all over the world, oil exploration is being carried out by seismic reflection. If you take India, several companies carry out operations in different parts of the country, not only on the land and also on offshore, right? In Godavari, Krishna Godavari basin, right? Bombay High, west of Bombay in Arabian Sea, in Kaveri basin. So, everywhere lot of investigation is being carried out, right? Considerable amount of survey has been carried out since last 70-80 years in different regions, right? Especially the notable ones are these companies. At these locations, we have done lot of investigations, and the country's premier organization for geology, which is the Geological Survey of India, GSI, have been carrying out investigations, especially in the Cambay basin right from 1955, right? And also in the Kaveri basin, right? And the other agency, which is the Oil and Natural Gas Corporation, right, has been carrying out investigation from 1957. This organization is producing oil from different locations of the India, right. Now, let us have a look into some other interesting case studies. This is one study carried out in Nigeria to understand the subsurface, especially for oil exploration. The diagram on the left hand side, that is this diagram here, shows the seismic cross section, right. That means we have created a image of the subsurface from the seismically reflected signals. The axis here is in meters. You can see we have investigated nearly up to 4 kilometers below the surface of the earth. From the seismic section, the geologists or geophysicists combinedly have interpolated these sections and annotated them. That means here you can see something like a canyon cut. What does it indicate? Possibly across this, that means this is north and south, there might have been a river running, and it has cut this. Subsequently, it got filled also. Similarly, you can, wherever you can see, right, here too I can see, right, something like a canyon or a river that has cut this, and also you see some channel would have been formed here too, right. This is how we interpolate the seismic section. Here too there are small channels, right. Here too I can see, right, some kind of V type of channels have formed. That means what has happened at this location is, in the geological past, the river has flown over there, brought in huge amount of deposition, right. Slowly the land has raised, right, due to continuous deposition from this depth, right, and it has reached the present day location. This is the present day ground surface. Broadly, by looking at this seismic section, we can see 4 different layers. This is the first zone. Here we don't see any river cut channels, right. Probably during this time there is a progressive formation of layers of sediments. So, this is the first zone. Then this is the next major zone, seismic zone, right. So, this is the first sequence, second seismic sequence, then there is a thin seismic sequence 3 marked by a major discontinuity, right, indicated in green color. Then there is a next sequence. So, this is how the seismic image has been interpolated, right, and they are also demarcated based on the velocity, right, based on the seismic velocity, right. And by looking at the diagram, we ourselves can draw some contacts. Based on this, on the right hand side is the interpolated geological section. Right. So, what you see is the interpolated geological section. How did we arrive at this section? All these drawings are made by looking at the diagram on the left hand side. However, here in this case it is not to the scale, but we can also make it. So, this is something like what you see here, right. So, this is how we have interpolated this and brought out the geological section, right. So, this study has been carried out by these researchers, right, and they have published this in a popular journal, Marine Geology, right. So, this is how the seismic reflection survey can help us to understand about the subsurface. So, in today's lecture, we had a look into seismic reflection survey. We continued with whatever we had seen in the previous lecture. Today, we had seen what is common depth point shooting, what is profile shooting, then what is fan shooting, and we had a look into some applications of seismic reflection survey. Broadly, seismic reflection survey is carried out to understand the deeply buried geological structures, which are hence indispensable in oil exploration. So, toward the end, I showed you this case study. We will continue to look into some more case studies in the next lecture. Thank you very much.